speaker. So the next speaker is Professor Nigel Richards from Cardiff University in Wales, in the United Kingdom. And he'll be speaking about a biomedical application or biochemical application of MOPAC. And I'll let him give further details of that. Is Professor Richards here? His camera and mic are on. I have not. Oh, there he is. I can't hear you, Professor Richards. I don't know if you're saying anything. I don't see your lips moving, actually, so maybe not. But I do see you.
Okay, can you hear me now?
Yes.
Okay, yeah. All right, my AirPods are giving up.
Oh yeah, I've had that happen. Their battery does not. They only last like 3 hours. Yeah, it's very problematic for a conference. I've had them die in the middle of conferences.
Okay, so I guess everybody can see my screen now.
Yep.
All right. And I'm going to take people through a fairly simple application of MOPAC. My group tends to be abusers of computational software, so we tend to use it to solve experimental questions that we can't solve by experiment. Anyway, so thanks for inviting me, and let me kind of get started here. This is a fairly simple problem compared to some of the things we've seen, but I think it illustrates some of the power of MOPAC. So we're very interested in how to make carbon-carbon bonds, and especially to make novel antiviral agents. And it turns out that a particularly good class of antiviral agents are these kinds of molecules which are nucleosides, but instead of having a normal carbon-nitrogen bond between the sugar and the nucleobase, we have a carbon-carbon bond. And these are much less common in nature, as you can imagine. And there are whole classes, a whole variety of these kinds of structures around, with antiviral and antibiotic properties. And we'd like to use biocatalytic methods to be able to put these carbon-carbon bonds together, and we would especially like to be able to construct alternative nucleobases and alternative sugars for a variety of reasons. So a few years ago, 3 or 4 years ago now, we got interested in the pathway that leads to these kinds of structures. And the key enzyme in this pathway, and this is what I'm going to be talking about today, is an enzyme we call 4T. And what that enzyme does is it basically takes this activated ribose 5-phosphate. We're not going to worry too much about the biochemistry, but basically the pyrophosphate is a leaving group. It generates essentially an electrophilic character to this carbon, so nucleophiles can attack it. And in this particular enzyme case, we're going to take a very strange kind of structure, a very unusual structure in biology, a pyrazole structure, a highly functionalized pyrazole, where we have an amino group and then 2 carboxylic acids. And what we're going to do is this enzyme is going to take these 2 precursors and is going to basically form the carbon-carbon bond, and is going to lose carbon dioxide in the process. And the mechanism is quite straightforward. I'm not going to bore you with all the chemistry, but the idea is very simple. You generate some kind of C+ here, or some kind of SN2 reaction that's still a little bit unresolved. And what we're going to do is activate the heteroaromatic ring to donate electrons to form the carbon-carbon bond. We then have to regenerate the aromaticity of the ring. And so we lose a CO2 molecule. And so that essentially drives the reaction to completion, essentially 100%. You form pyrophosphate and you lose CO2. So the mechanism of this system is fairly straightforward. And we were particularly interested in this because we thought we could use time-resolved crystallography to watch this reaction happening in very short timescales. But before you can do that, you have to be able to understand the system. You have to be able to know what you're looking at when you take a diffraction map, electron density map from a time-resolved crystallography experiment. And so we'd like to be able to see snapshots of this chemistry in order to understand what kind of maps they give as part of interpreting the time-resolved crystallography. And so, you know, being enzymologists, we do the same kind of boring things other people do, right? We change the structure. And what we were interested in the enzyme to find the functional residues, and we were particularly interested in finding variants of this enzyme which would react slowly, which would give us the best chance of trapping intermediate structures during the catalytic reaction by X-ray crystallography. And so there are two variants that I would draw your attention to, where we change a leucine into an alanine. That slows the chemistry down by about fourfold, give or take a bit. And then when we change a threonine into a valine, that slows down the chemistry considerably more. And so we thought, okay, we could begin to trap what was going on in the enzyme with these variants. I also want to point out the kcat value, which is about 1 per second, give or take a bit. You know, trying to get better accuracy or whatever is a waste of time. And that corresponds to a barrier of around 13 kilocalories per mole, give or take a bit, for the rate limiting step. And the rate limiting step is almost certainly, I mean, I have evidence for this, but is forming the carbon-carbon bond. So what we'd like to do is understand the chemistry, and we'll see why that 13 kcals per mole is important in a minute. So yes, our strategy was correct. We were able to take this very slow variant, and we were in fact able to trap the initial complex, showing us how the PRPP, the activated ribose ring, is positioned within the active site relative to the pi system of the aromatic ring, the pyrosol. You can see that we don't know where the hydrogens are in these structures. They're not well enough resolved, but essentially one of these nitrogens will have an NH bond. But basically that's what we see from the density maps. Now let me make sure I'm on time here. Yes, I'm going well. So we will be able to use that variant to trap the starting structure. And it's kind of intriguing because in fact, these two carbons here are positioned in very similar distances away from the leaving group. This carbon here is the one that's going to react. But essentially, we believe the closest one reacts. Now, we were also successful in using the slightly more active variant to trap the product. Okay, so we basically were able to get the crystal structure where we see the product of the reaction after the carbon-carbon bond is formed. And here's the pyrophosphate, and there's a magnesium in here, which we're not showing. We have density. We know where the metal is that's involved in this reaction. So we have these two structures, everything's looking good, and then we notice something that was a problem. And the problem is in the two structures, and I wouldn't look too closely here, I would look at this. In the two structures, the orientation of the amino group on the pyrazole ring is different. So in the Michaelis complex, it's kind of pointing away from us. In the product complex, it's kind of pointing towards us. And now we have a problem. The problem is which orientation is actually the correct orientation. You know, are both of these structures correct? My colleagues didn't seem to think of. I think that was true. I've not shown any of the data, but there are extensive hydrogen bonding interactions that are formed between this ring system and the enzyme. And so, you know, this is the kind of thing that goes on in crystallography, right? You trap what you trap. You get the crystal structure of what you get the crystal structure of. But the density is definitely more consistent with this orientation of the ring. So we really wanted to resolve which one of these two orientations was the most likely to be correct. and to begin to understand what was going on in the chemistry. And since we were in a race to publish this data, we didn't want to hang around and spend months doing QMMM calculations and sampling and free energies. We wanted a very fast, rapid way of assessing the orientation of this ring for the chemistry. The other problem, of course, that is obvious, and I've already kind of alluded to it, is we'd like to know where the hydrogens are in this system. We'd like to know which one of these nitrogens has the NH bond and which one is the nitrogen with the lone pair. And there's some technical reasons to know that. So we turned to MOPAC. I really wanted to do this with Mozyme, actually. I really wanted to do the whole enzyme. It's about the right size for a decent Mozyme calculation. We had lots of water molecules in the structures, which I've been taking out for clarity, but essentially we know that water is playing a role in the chemistry that's going on in the enzyme. So we wanted to leave waters in. And I called up my friend Jimmy Stewart, and I said, Jimmy, here's the perfect problem for Mozyme. And he kind of went white and said, well, maybe you'd like to do it on smaller structures instead because of multiple minima and locating transition states, et cetera, et cetera, et cetera. So we decided that we would actually use the active site modeling in MOPAC because we would get, it would make the calculations technically more reasonable. And so we set up a series of calculations in different ways. And what we're going to do in these calculations, I didn't want to spend a lot of time locating transition states. And in these very complicated systems, it can sometimes be tricky to find transition states. So what we decided that we would do is the decarboxylation step, the step that regenerates the aromatic system, almost certainly has a barrier which is around thermal energy or less. I mean, it should be a very rapid reaction. So what we decided is the transition state would actually look more like the pre-decarboxylation intermediate. And we would use the pre-decarboxylation intermediate, if you like, to begin to model what was going on. And so we basically, the R group here is the ribose ring. Okay, and we set up basically the starting structures. There are 4 possibilities. Orientation of the Michaelis complex, orientation of the Michaelis complex with the NH here. Same orientation, moving the NH. Then the reorientation of the structure within the active site model, and that would lead to essentially these kinds of intermediates, pre-decarboxylation intermediates. And so MOPAC is quite easy to set this up, to use this. And of course, we want the energy difference because, you know, we may well have one of these structures may have a lower energy in the complex. But of course, what is important in catalysis is that it's the energy of activation that we wanted. We want the difference in energy between these systems as we go from reactants to the products. And so we basically used the heats of formation to do this, set up a whole bunch of things. Let's see, these energies of activation. I'm sorry, the activation free energy is actually higher than I said it was. Anyway, let's just move on. So what we were looking for here is we were looking for the one with the lowest energy of activation as we moved from starting material to product. And in fact, it turns out to be, I don't want to go into detail because I've almost run out of time. It turns out to be the orientation in the Michaelis complex, which is giving us essentially the lowest energy of activation to go to form the CC bond. And so that fits in with a number of other experimental observations and work we've done subsequently. And that's the take-home message I wanted to leave with people with today, that, you know, all of this benchmarking is nice and you can do lots of things and you can do lots of comparisons, but at the end of the day, we want to solve scientific problems. And MOPAC is a very, very straightforward way of solving scientific problems. And I should point out this information is useful because we're interested in making analogs. We're interested in looking to see if we can vary these kinds of molecules to generate new kinds of structures. And we're in the middle of that right now, looking using calculations to try and understand how electronic differences in the heterocycle will affect reactivity and the energy of activation. So that's really what I wanted to tell you about today. These are the guys, well, this guy here was the kind of guru who actually told us how to do everything. But the guy who did the work was my postdoc Ashish in Cardiff, and the crystal structures were done at the Rosalind Franklin Institute by my collaborator, Jim Naismith, and his PhD student, Wembo Lee. Okay, so I think I've said all I wanted to say, and I'm happy to take questions. Let's see if I can get out of here.
All right. Thank you, Professor Richards, for your talk. Are there any questions? And I can lead with a question. So are you using the transition state search features that are available within MOPAC itself, or are you using MOPAC to generate potential energy surfaces?
We were just basically interested in using MOPAC to look at energy differences between different possible structures. We were not interested initially in looking for transition states. The problem with these systems, of course, is that you have multiple side chain conformations in the active site, and so you can generate transition states, and then you can use the IRC to kind of connect them into starting structures. But the system is quite complicated, and so we were looking for a result very quickly, actually, because we were in a race to publish, which we won, in case anybody's interested. But in principle, we could do all of that. And in fact, but right now, I like to keep things very simple right now, because we're trying to screen through a whole bunch of heterocycles to see how electronic structure is affecting what goes on in the active side. So we have not used anything sophisticated, but we would obviously consider it. The thing I really want to do is to use Mozyme to do the whole system quantum mechanically, and maybe one day I will. We'll see how that works out.
Did the greater costs reduce your throughput? Was that the barrier? Like, what was the most immediate barrier?
Yes. We wanted to do a whole series of systems very quickly, and we didn't want to get stuck in local minima or transition state searches, which were going to be require a lot of validation. As I say, that's why we wanted to approximate the transition state energy by the energy of the intermediate, because they're almost certainly extremely close. This is a very endothermic reaction, losing the aromaticity and making the CC bond.
Okay, so it wasn't necessarily the cost per calculation, but just you're dealing with a much more complicated potential energy surface, and you just didn't want to have to rationalize it.
I see. Yes. So the calculations themselves don't take, they didn't take that long to run. You're right. So in terms of computational cost, there's not much, but I didn't want to get into complication, and I really wanted answers very quickly, and I didn't really want to have to do the conformational sampling that I knew I'd need to have to do a really thorough study. So that remains to be done in the future. We were much more interested in resolving this crystallographic problem and getting the structures published, because there's some interest in these enzymes, it turns out.
All right. Are there any other questions for Professor Richards? If not, we can move on to the final speaker for the day.